So if you remember in the last video, I was starting to talk about this whole idea of trying to find some regression model, okay, and trying to form an optimization problem for a particular regression model. So remember, the optimization problem is basically trying to maximize or minimize something. So say, for example, if we have, we have RP, which is the regression model, okay, in terms of some data P, and that would have been given by something in terms of our variables. So our variables are basically our coefficients. Those are the things which we're trying to find. We're trying to find the coefficients. So I'm setting it up as a nonlinear programming problem because, or linear programming problem, basically an optimization problem, because the first step is to define my variables. Well, what are my variables? It'll be the coefficients. It'll be the coefficients. So for example, I might have x1 times some data P plus x2, for example, right? Or I think I wrote it in the last video the other way around. So that's a linear regression model. Yeah, so I want to try and find what x1 and x2 are. Or I might have, for example, a regression model that looks something like this, which is x1 times p to the power of x2. Basically, what I'm trying to do is I'm trying to find what these numbers here are. So I'm setting up an optimization problem to try and find out what these values are. Now, if you remember when I was trying to define the method of optimization, well, the first step was to define the variables. Well, we did that. The variables are just simply the coefficients, right? Just simply the coefficients for this particular problem. Okay. Then if you remember, the second step was to define the constraints. Okay, so define the constraints of the particular problem. Well, in this case, there aren't actually any constraints, because all we're just basically trying to do is form what the regression model actually is. So we don't normally have any limitations on what the coefficients are because we're trying to fit it to the data. I suppose you could count, that they have to fit the data as a constraint, but we can't really describe that mathematically. So we tend to just ignore the step 2 for finding a regression model. Okay, so step 3 then. So step 3 then was to try and find the objective function, the thing which we have to either maximize or the thing which we have to minimize. Well, the objective function is actually something what's known as a residual. The objective function is what's known as the residual. So the objective function is basically trying to find the quality of fit. So in other words, we want to, if you have kind of a straight line graph, so let's say, for example, we end up with some data that looks like this. So this is our first point of data. This is our second point of data. So let's say we have a bit of data with let's say our set of data looks like this, and we find that the regression model, the best line of best fit to go through the middle. Of course, this could equally be a curve, by the way. We could have some data that looks like this, and we have to fit it, and the way to fit it is using a curve. Okay, and that would normally be a non-linear case, but I think it's easier to see with the linear regression model first. So basically, the idea is that we want to try and minimize the distance between the points and the actual line. And that point there, I mean, you probably know that as error, I can't remember what we called it at A-level in physics, I'm thinking. But anyway, basically what we're trying to do is we're trying to minimize that distance there. Because this is the point where we're basically saying that, the point should lie on that line, at that point there. So say, for example, this corresponded to, let's call it 1, let's call this 2, and let's call this 3. So let's say that, x should be 1. So at the point x equals 3, let's say, the point x equals 3, we're basically saying it should lie at this value here. But instead it lies up here. So according to the regression model, it should lie here, but according to the actual data says it lies here. Right, so basically the idea is that we want to try and minimize these distances in here. We want to try and minimize these distances, and these distances give us a special name, and those distances are called residuals. Those distances are called residuals. So if you want to follow the method of optimization, because this is effectively an optimization problem, we're trying to find out what the coefficients are that fit a particular data set. Well, the third step, the objective function, is given by the residual, and this is, if you like, the quality of fit. So how well the line of best fit fits the data points. Okay. So how can we define the residual? Well, the residual is quite straightforward. It's quite intuitive. Okay. This is the actual data. And I'm going to call the actual data Qi. So let me just scroll up a little bit. I'm going to call the actual data. Let's call it Q. Okay, so I'm going to call it Q. This is the actual data, okay? And the fitted data, well, the fitted data is given by this line of best fit. So this line of best fit, and this line of best fit is given by the regression model R of P. Okay, so this is actually what's known as the residual model. So fairly obviously, it's the difference, yeah, if I just get rid of some of these annotations, it's the difference between the actual data, so this is the actual data, and the point where we should be lying on, where the line of best fit says it should be. So this distance in here is what's known as the residual, okay? And this is fairly obviously the difference between the actual data and the fitted data, if you like, or the data which it says it should be. So this is the residual. Okay, the residual is given by Q minus RP. So Q is my actual data. Oops, my actual data. So the data which I know it is. This is the data which I've gone out and collected. So I know that the data should be looking like this. And this is what's known as the fitted data. So I want to come up with some kind of fitted function, the regression model, and that's basically the fitted function. Now we normally give it sort of little subscripts. So this residual is often given E, purely because we can't use R, because we've already said that R is our regression model. Okay, so E. And we can have lots of different values for this. We can have lots of different values. So we can have like, value 1, let's say, so Q1. So that would be sort of Q1 might be, for example, X1, Y1. Okay, so that might be, our first set of coordinates, and Q2 would be our next set of coordinates. So basically the idea is that we can go right the way along this line. So this is our first point, this is our first point, this is our second point, this is our third point, okay? So in other words, we need to introduce this little I notation. And this little I notation just simply means, okay, you start at the first point. You start at the first point, you look at the actual point where the actual first point should be. Sorry, this should be in here, where the actual first point should be. So in other words, up here, okay, and then you look where the line of best fit says the data should be. So down here, okay, and you just subtract the two, and then you work right the way along. So this is what this little I notation just means down here. So for example, if our residual function, if Rp was given by x1p to the power of x2, okay, then our residual function EI, is given by our actual data, QI, minus this, which is our residual function. So x1 pi, we just replace our p in here with pi, okay, pi to the power of x2. Okay, so hopefully that makes a bit of sense.